Hi, and welcome back. We're in chapter 8 now. Dynamics number 2, it's motion in a plane. We just finished Newton's third law in the last chapter, and the previous two chapters, chapters 5 and 6, we studied Newton's first and second laws. Today, there is nothing really new to learn except just applying Newton's laws in 2D, in two dimensions. Newton's second law makes no distinction between one-dimensional motion, two-dimensional motion, or even three-dimensional motion. Simply it says the net force on an object is equal to ma. So, remember the theme in the first few chapters where we just did kinematics without Newton's laws. It was, give me the acceleration, I will tell you what the future of the object will be, meaning where it will be located and what would its velocity be. With Newton's laws, basically, well, give me the force, I will give you the acceleration. And we're doing even more than that. We're saying we determine the forces. We use those forces to determine the acceleration, and then we will use the acceleration to determine the fate of the object. So, that's what we're going to do. We're going to look basically a bunch of problems today. And lots of them are in circular motion. And so let's look at the first problem here. It comes from example 8.1 in our book. It says a small rocket for gathering weather data has a mass of 30 kilograms. So this rocket has a mass of 30 kilograms. It generates 1500 newtons of thrust, meaning the rocket can be pushed. You can imagine it's kicking gases out, and then the gases will push the rocket forward with a force of 1500 newtons. So it's a constant force, 1500 newtons. And then it says, on a windy day, the wind exerts a 20 Newton horizontal force on the rocket. If the rocket is launched straight up, so the rocket is launched vertically, so the thrust is in the vertical direction, it says, what is the shape of the trajectory, and by how much has it been deflected sideways when it reaches a height of 1 kilometer. And then here they make a comment and say, assume that the rocket's mass is constant, because the rocket goes much higher than this. And so, yes, it will lose a little bit of mass. The mass will not be 30 kilograms at the end, but let's assume it's constant. We will worry about that later, the motion, when it loses mass, when we discuss momentum. I think that would be what? Chapters 9 and 10 are for energy, and chapter 11 will be for momentum. So let's take a look at this problem. So before we go, obviously we have to apply Newton's basically second law. All right, so I will draw something here. Okay, let me get my chalk. All right, that's okay. So here is a rocket, just an object. And to figure out the motion of the object, you have to figure out the acceleration. And to figure out the acceleration, you need to apply Newton's second law. So you have to find the forces. So the rocket is launched in the upward direction. So here is my y direction, I would call it upward, and then here's the x. It starts with an initial velocity equal to 0, and let's say the location is at the origin. So this is the location 0, 0. This is the x-axis, and this is the y-axis. All right, it starts there. So what are the forces on it? Well, there is the thrust. It's being thrusted upward. F thrust. Of course, it's on Earth, so there is gravity, mg, force of gravity. And then there is wind sideways, so the force due to the wind. I'm just writing the whole word, F thrust, F wind, and mg. I could have written it Ft for thrust and Fw for wind, but let's just write it as all. So we'll apply Newton's law in the x direction and then in the y direction. If you like, the net force here, this mg, the force due to gravity, the net force, let me just write it maybe once more. The net force will equal to the force of the thrust plus the force of gravity plus the force of the wind. Okay, so the net force is, the force of the thrust is in the y direction, so it is the force of the thrust, that's the magnitude. The direction is in the positive y direction, so you put j hat. The force of gravity has a magnitude of mg. It's directed downward in the y direction, so it's in the j hat direction, and it's downward, so there is a minus sign. The force of the wind is in the x direction. It has a magnitude f, wind. It's in the x direction, so that's I hat, and it's positive. All right, so that's that. So now, this force, you can break it down into two forces. One is in the x direction, and one is in, and two parts are in the y direction. So we'll say the net force, this is how we usually write it, the net force in the x direction will equal to the mass times the acceleration in the x direction. The net force on the rocket in the x direction will equal to the mass of the rocket in the x direction. I'm sorry, the mass of the rocket, it's a scalar, and times the acceleration of the rocket in the x direction. Okay. So the acceleration of the rocket in the x direction will be the net force in the x direction divided by the mass. The net force in the x direction is the force of the wind. So it's the force of the wind divided by the mass. So the x, then, we have, this is constant acceleration. So we know that x final is equal to x initial plus v initial in the x direction times the time plus 1/2 of the acceleration in the x direction times the time squared. And so the initial position is 0 in the x direction. It starts at the origin. It starts from rest, so the initial velocity is 0. So this is a 0 and a 0. So it's just 1/2 at squared. So x will equal to 1/2 times the acceleration in the x direction, which is, I would just write it, the force of the wind, F wind, over m times the time squared. All right, so let's box this one. Okay, let's box it. Next, I will use a different color. Let's use this one. The net force in the y direction will equal to the mass times the acceleration in the y direction. And so the acceleration in the y direction will equal to the net force divided by the mass. It's the net force in the x direction, in the y direction divided by the mass. The net force in the y direction consists of the force of the thrust in the positive y direction and the mg in the negative y direction. So you get the force of the thrust minus mg. Minus mg. And so we can write that that y, this is motion at constant acceleration again. So y will equal to y initial plus v initial in the y direction times the time plus 1/2 of the acceleration in the y direction times the time squared. And so you get y will equal to, the initial position in the y direction was 0. The initial velocity is 0 because it started from 0 speed. And then, so you just have 1/2 at squared. So you get y will be 1/2 the acceleration in the y direction, which is the force of the thrust minus the mg divided by m. The force of the thrust minus mg divided by m times t squared times the time squared. So 1/2, this is the acceleration times the time squared. That's good. So now, are we done? Well, let's see. It says goes straight up, and then it says, by how much has it been deflected sideways when it reaches a height of 1 kilometer? Actually, before that, it says, what is the shape of its trajectory? So what's the shape? Does it go in a line? Does it go in a curve? So if I know the position, how the y position depends on the x position, we will be able to do this. Then we just have to eliminate the time. I have time here and time here. So t squared will equal to 2x times m divided by f wind. So I'm going to replace the time here by 2x times m divided by f wind. So let's see. So you get y will equal to 1/2 of the force of the thrust minus mg divided by m times t squared. And I'm going to replace this t squared by, just solve for t squared here in terms of x. It's 2x times m divided by F wind. So it's 2x times m divided by F wind. That's t squared. You know this mass cancels, and we get the y. Oh, and the 2 here and 1/2 here cancels. And you just get y will be F thrust minus mg divided by F wind times x. This is a constant. F thrust is a constant. It's just some number. It's 20 newtons. Mg is 30 kilograms times 9.8. The force of the wind is 20 newtons. I'm sorry, the thrust is 1500 newtons, not 20. So anyways, those are just numbers. So you just have y equals to a constant times x. How would you graph that on the xy plane? It's just almost half of each other. It's just a line. This is the equation of a line. This is x, this is y. So y depends linearly on x. So it would be a line, it would be a straight line. And then it says, because the rocket, I'm sorry, where am I here? It says, when it goes to a height of 1 kilometer, how far to the right has it been deflected? Meaning, when y is 1 kilometer, 1,000 meters, what is x? So I will solve that right here. So we get, actually, let me just reduce this. So you get y will equal to F thrust, that's 1500, minus mg, so you have 1500 minus mg, that's, the mass is 30 kilograms, gravity is 9.8, and then you have here 20 newtons for the force of the wind, that's 20, and then the whole thing times x. Sorry, I'm getting tighter here. So you get y will equal to, let's do 1500 minus 30 times 9.8, and then the whole thing divided by 20. Let me get my calculator here. I don't calculate things. If you notice, a lot of times when I do a problem, I purposely, when I look at the book, I write it, and I don't look at the solution. So you see me struggle through the solution and make mistakes. And that's the process you should be going through, okay? Nothing works perfect in the first time, so expect to make mistakes. And sometimes to go faster, I will read the problem, do the solution ahead of time so that you see me going faster. Anyways, so let's calculate this. So I get 1500 minus 30 times 9.8, and then you divide that result by 20. So that's 60.3. 60.3 times x. So this is the direction. So let's solve for x. So we get x will be y divided by 60.3. And they want to know what is x when y is 1 kilometer or 1,000 meters. So we get here when y is 1,000 meters, you get 1,000 over 60.3. That's about 16.6 meters. 16.6 meters. So it will rise 1,000 meters and only move 16 meters or 17 meters to the right. So most of the motion is upward. Because, I mean, this is far greater. The thrust minus mg is far greater than the 20 newtons due to the wind. And so that's why most of the motion will be upward as you want. Okay. All right, let us look at our next topic here, which is circular motion. Make sure the camera is working, okay? Yes, it is fine. So, uniform circular motion, we have derived this back in chapter 3 probably, or 4. that the acceleration for a uniform circular motion was v squared over r. So if you're going in a circle, let me draw my circle here. Just to remind us, I have a circle, and the circle has radius r, and you're going around the circle counterclockwise or clockwise, doesn't matter. And you're going at a certain speed. The speed is constant. And so we call the time it takes to do one circle the period, capital T, we call it the period. The period. Time to do one cycle. Time for one cycle. That's called the period. And the frequency is 1 over the period. Frequency. Of course, the period is a time, so it's measured in the standard units of seconds. So the frequency would be 1 over time, 1 over seconds. It's also known as hertz. So if that's the period, then the speed is the distance traveled divided by the time elapsed. If you go around the circle once, the distance traveled is 2 pi r. The time elapsed is the period, because that's the time it takes to do one cycle. And so the speed would be 2 pi r, 1 over the period, because it's in the bottom, is called the frequency. Okay? And then if you remember, we also defined the angular speed or angular velocity. So the angular speed was the amount of angle you make divided by the time. It was omega, that's the angular speed. It was the angle you do over the time. The angle you do when you go around the circle once, in radians, it's 2 pi. That's the angle over time. And then the time it takes to do that one circle is the period, so it'll be 2 pi times the frequency. So you got 2 pi frequency here, so that's omega. So V is also equal to omega times r, because 2 pi f is omega, and then there is an extra r here. So you get V. And then we also said, if you're going around the circle, there is an acceleration. Because you're changing motion constantly, right? Newton's first law says if the net force is 0, you should be going along a straight line with constant speed. But here, sure, the speed is constant, but you're changing your direction. If you're changing your direction, then there must be a force. You want to go straight, somebody has to keep pushing you toward the center. So you want to end up here, but somebody has pushed you to keep you on track. And then once you're here, you want to keep going straight, somebody has to push you, keep you on track. So there is someone pushing you toward the center, causing an acceleration toward the center. And that force that pushes you is related to the acceleration, because the net force is equal to the mass times acceleration. So we derived the formula for the acceleration. This is called centripetal acceleration due to the change in direction of motion. It was v squared divided by r, and if we put, instead of v, we put omega r, and we square it, and we divide by r, we will get omega squared, r squared divided by r, which is omega squared times r. That was the acceleration. So I put here, for uniform circular motion, the acceleration is v squared over r, and it's toward the center. And then we create this coordinate system that our book has. And that coordinate system has, instead of x, y axes, they have the r, first of all, they choose the origin to be where the object is located. So let's say, here's our object going around the circle, and here it is. Here's our object. And let's say it's going around the circle in the counterclockwise direction. Here's our object. This is the center of I'll draw an X, because center of the circle. So we're going to define the origin to be where the object is located. So here's the origin of our coordinates. Secondly, the r-axis, called the radial axis, it points from the particle, from the object, to the center of the circle. So if our object is here, our radial axis is in that direction. If our object is here, the r-axis will be in this direction. It's called the radial direction. So this is the r-axis. That's the r-axis. Okay, great. Then we have the t-axis, the tangential axis. It's tangent to the circle and it points in the counterclockwise direction. So we have to have a positive sense for motion. We usually consider counterclockwise to be positive, clockwise to be negative. So we define our t-axis, positive t, to be in this direction. Okay, to be in that direction. And then the z-axis, which we usually don't need, but we define a z-axis to be perpendicular to the motion, so out of the board, if you like. So it would be out of the board. So we have three perpendicular axes, mutually perpendicular to each other. So that's the z-axis. So we say the acceleration is along the r-axis. The velocity is along the t-axis. Okay, the velocity is along the t-axis. All right. So let me look here at. So those are the axes. That's really terminology. It would be very clear and intuitive when we start solving problems. So let us solve look at this problem here. 8.2. It says you have an energetic father, and this father places his 20 kilogram child on a 5 kilogram cart to which a 2 meter long rope is attached. So let me draw a cart with a child. Actually, I'm not going to draw a cart with a child. It will be just like this. All right. This is the cart plus the child. Here are the wheels of the cart. Right? The wheels of the cart. And it will be child plus cart, so that's 25 kilograms. So the mass is 25 kilograms. So the mass that's the mass. It's 25 kilograms. Fine, okay. Then it says a 2 meter rope is attached to this cart. So here is a 2 meter rope. Rope is 2 meters. Is attached there. Okay. The father then holds the end of the rope. So the father is standing here and holding this rope. And then spins the child and cart in a circle. So as you can imagine, the father is spinning them this way. Hopefully not that way. You don't want to spin. I mean, you might fall. So they're on the floor and the father is spinning them that way. So when they're here, they're coming towards you and then going around. When they get there, they're going into the board and coming like this. So this is the r-axis, if you like. This is the r-axis. And then the tangent axis, it points in the counterclockwise direction, tangent. So we're going counterclockwise, and it's tangent. So the t-axis is pointing towards you. And then the z-axis is perpendicular to the motion that way. All right? All right, that's fine. I don't need that. And then it says the rope has tension of 100 newtons. And then it says how many revolutions per minute does the cart make? Assume friction is negligible. Okay. So as the cart is going like this, what are the forces on it? Well, it's standing on a floor, so there is the normal force. And then there is the force of gravity. Okay, is that it? Well, it's attached by a rope, and ropes pull, and so there is tension in this direction. There is the force of tension in that direction. And there has to be, because you're going in a circle, you need somebody to pull you toward the center. And the force that's pulling you toward the center is that tension force. Notice the normal force and mg, they act in that z-axis. I'm interested in the motion along the r-axis, the radial axis. So it's the tangent, the tension that is causing that. So the net force equal to the mass times acceleration. The net force in the radial direction, along the r-axis, is equal to the mass times acceleration along the r-axis. So let's write it. The net force in the radial direction would equal to the mass times the acceleration in the radial direction. What is the only force acting along the radial direction? It's the tension, equal to the mass times acceleration. What do we know about acceleration? You see, for linear motion and so on, usually you don't know ahead of time the acceleration, but this is uniform circular motion. We know ahead of time that the acceleration is v squared over r, whatever the v is, v squared divided by r. So this will enable me to find V. So I get V will equal to R times the tension divided by the mass, and you square root that. That's V. Here they're asking how many revolutions per minute are we making. That's the angular velocity. They're really asking for omega. Well, V is equal to omega times R. Okay? Omega times R. Therefore, omega will be V over R, so I have to divide this by R. So omega will be R capital T divided by M square root, and you have to divide this by R. When you take the R inside the square root, it becomes R squared at the bottom, but it cancels the R on top, so it becomes the tension divided by R times the mass. That is omega. Let's calculate omega. Notice, when we get omega here, we will get radians per second, the standard units for omega. The angle per unit of time, the angle in standard units will be in radians. So, the tension, they're saying, what's the tension here? They are saying, I forgot. It should have said. I can't find it. If the tension in the rope is 100 newtons, the tension is 100. What's the radius of this circle? They're telling us that the rope is 2 meters long, so this, the circle is 2. The mass is 25 kilograms. And I square root this. 100 divided by 2 times 25, that's radical 2. It's the square root of 2. So that's like approximately 1.41. 1.41, I think 414 radians per second. Radians per second. Let me double check. I forget my square root of 2. It's an irrational number, I should know. 2, 1 power, 1.4414. Yeah, that's good. Approximately. And so I have omega is 1.414 radians per second. They want RPM, revolutions per minute. Well, there are 60 seconds for every 1 minute, and there is 1 revolution for every 2 pi radians. So if you like, you can cancel radians by radians, and rev, rev actually we want it. So rev stays there, 1 rev. You cancel seconds with seconds, and you just have revs per minute. So basically what? You multiply by 60 and divide by 2 pi. So let's multiply by 60, and we divide by 2 pi. And I get about 13.5 revolutions per minute. And I need to double check that with the book, because I don't want to make a mistake and then watch the video later and then I can't correct it. So it's at about 14, yeah, 13.5 something. Yeah, great. So the child here is being spinned along with the wheel, and the father is spinning them. They make 13.5 turns per minute. All right, that's okay. I don't know if that's fast or not. 13 something per minute. That's actually fairly fast. Yeah, that's fairly fast. That's why they say an energetic father. All right, I will see you in the next video. Continue with circular motion.